Okay, hello. My name is Anthony, and today I'll be presenting my findings this summer on my investigation of the catalytic performance of supported vanadium oxide catalysts in the partial oxidation of methanol. So, the motivation for this research stems from one of the biggest goals of recent times to find a reliable and renewable replacement to current fossil fuel derived energy sources to reduce the emission of greenhouse gases and maintain a sustainable circular carbon economy. To make this goal possible, attention has been brought recently to second generation liquid fuel additives, one of which can be produced from methanol derived from biomass derived syngas. The fuel additive polyoxymethylene dimethyl ethers, shortened to OMEs, are produced through means of the catalytic reformation of methanol. OMEs are valuable in the sense that they are non-toxic and are completely renewable, as the only other required reactant is oxygen. Moreover, because of their high oxygen content and cetane number, they allow for more efficient combustions and reduction of soot formations in diesel engines. In figure 1 here, we have the expected reaction pathway using a supported metal oxide catalyst. Metal oxide catalysts are useful for their valuable ability in providing both an oxidative and acidic catalytic site. Our overall goal is to form OMe1, that is, an OMe oligomer with one formaldehyde in the circle shown here, by following the redox catalyzed reactions in the blue and the acid catalyzed reactions here in the orange. The initial partial oxidation of methanol, this first step over here, is to formaldehyde, is a kinetically relevant step that has been studied in the past. However, the focus of this investigation is to build upon previous understandings of this step and to define ways in which the production rate of OMe1 can be controlled from this step, which is called the oxidative dehydrogenation reaction, shortened to ODH. The specific catalyst used in our kinetic studies is vanadium oxide supported on titanium oxide at a weight loading of 10%. Figure 2 outlines the catalytic mechanism for this ODH step in a gas phase reactor. The first step here involves the adsorption of methanol from the gas phase onto the oxidative site of the catalyst surface. The next step is the hydrogen abstraction from the methanol. Once this CH bond has been cleaved, it forms formaldehyde, which can then desorb off the surface of the catalyst, leaving our two hydroxyl groups here. The catalyst then promotes these hydroxyl groups into a water product that desorbs into the gas phase, creating a gap in the catalytic structure, denoted here. In the last step, the catalyst is regenerated using the oxygen gas fed into the reactor and thus completing this ODH cycle. Using a Langmuir-Hinshelwood model for heterogeneous catalysis, we can derive a rate law for this reaction. In this model, we expect that the reaction dependence is close to 0 with respect to oxygen, as it does not directly participate in any of the kinetically relevant steps in this cycle, and is in between -1 to 1 with respect to methanol, depending on the surface coverage of methanol on the catalyst. Our test shown in figure 3 showed that the ODH rate has a 0.36 order dependence with respect to methanol and a 0.12 order dependence with respect to oxygen. And this fits very close with our hypothesized understanding of the reaction mechanism. Our next set of studies involves understanding the effect residence time has on the selectivity of the products and how the approach to this reaction to completion and equilibrium can help us optimize the process. To change the residence time, we change the input flow rate measured as gas hourly space velocity, that is GHSV, to the reactor. So as GHSV goes down, the residence time of reactants gets larger. And as GHSV approaches to completion and equilibrium, that is, as GHSV approaches to 0, we'll be getting to the reaction completion and equilibrium condition denoted in the green oval here. The results of this study show us that the selectivity of methanol to OMe1 increases from 11.2 to a maximum of 73.8. This would mean that as residence time increases, that is going left on this x-axis, selectivity to OMe1 will decrease. To verify this hypothesis, a simulation was done in Aspen Plus using the equilibrium reactor R. Gibbs, which works by calculating the chemical equilibria of a defined set of components by minimizing the Gibbs free energy of that reaction mixture. The result of this equilibrium run show us that water and carbon oxides become the most abundant species as the reaction approaches completion and equilibrium, and all other products, especially OME1, have much lower selectivities and are not equilibrium favored products. This validates our hypothesis that OME1 selectivity is much more favored at lower residence times, that is, at high GHSVs. Our future research on this study involves understanding how the synergy between oxidative sites discussed and the acidic sites change for different catalytic structures, compositions, and reactor regimes, and how all this information can be used to further increase our control of OME1 production. Thank you.
Thank you for your presentation. Judges, if you have any questions, please feel free to ask.
Yeah, here, this is Charles here again. Anthony, very cool work. And you mentioned that the vanadium pentoxide coated on titanium dioxide. I wonder that what is the role of titanium dioxide other than as a supporter?
Yes, so the supports in metal oxide catalysts creates the this bond shown over here for the active site, the vanadium oxide to the titanium oxide, is the bond that essentially is most playing in the reaction role. In the case of this reaction, we could not discuss it in the scope of this research, but the titanium oxide gives us our acidic sites, which will be used to catalyze the reaction shown in orange.
So actually titanium also participate in the reaction? Yes,
yes it does.
One more question here. What type of control do you have in terms of morphologies or crystal size of vanadium pentoxide?
So the vanadium pentoxide, how it can be created through different means. You can create polymerized or isolated different compositions. So depending on that, it would be an important way in being able to test how many active sites and the proportionality of each active site to each other, because this will then change how your most abundant reactant intermediate will be absorbing onto the surface. So depending on how it is created using either liquid to solid catalytic deposition or vapor gas deposition, you will have different site structure which will favor certain products to absorb in different ways.
Excellent, thank you.
Anthony, it's Professor Evans. Do we have time for one more question? I'll take that as a yes.
Yes, she was muted.
Yes. So I didn't quite follow the connection between and the reaction mechanism. You indicated that the predicted reaction orders were to the 6th and the 12th power, and that was consistent with the mechanism. If I heard you correctly.
Oh no, sorry, I meant to the 0 and in between -1 to 1 power for oxygen and methanol, respectively.
Okay, then I misheard that because I couldn't quite.
So I'm sorry for cutting you off. It's just that those were our hypothesized ones. The actual ones came to 0.36 and 0.12 for methanol and oxygen, respectively.
I see. And why would methanol be hypothesized to be a negative correlation to the -1 power? Why do you think more methanol would give less formaldehyde, if I understand what you're suggesting?
Yes, so if more methanol becomes abundant on the surface, there will be less of the sites, these abstraction sites for this kinetically relevant CH cleavage to occur. So as you have more methanol on your surface that is absorbed onto it, this reaction will proceed slower and slower. And you would also need the configurations done in such a way that your sites are exactly next to each other. So in an ideal Langmuir catalytic heterogeneous catalytic surface, these are all created equally. However, we are also trying to consider that not all of these sites are created in ways that give the same kind of activation to this CH abstraction. So that's why we predict negative orders depending on the surface coverage of methanol on the catalyst.
Very good, thank you. Do we have time for one more question?
Yes.
Take that as a yes.
Sorry, I was muted.
So for the Aspen simulations of equilibrium, I didn't quite follow. Is the reaction methanol fully minimizing its free energy? Is that what you're looking at? And that's why you end up with CO2 and water? Or are you looking for some intermediate state?
Well, the goal is to, so in the Aspen simulation, we define all reactants and products, and Aspen uses a set of equations to minimize the overall the Gibbs free energy of this mixture. So it's not necessarily with respect to methanol, but it would be for the overall mixture. We use a Peng-Robinson equation of state for an unideal gas mixture, and this accounts for all enthalpies of mixing and all reaction conditions as well. So it is creating the overall minimized global Gibbs free energy minimum.
And do you find it surprising that if you take an organic and react it with oxygen that you end up with water and CO2?
No, not at all. So, this is as expected that this step, because if we go over to here, it is expected that the methanol will fully oxidize to the carbon oxides and water. It's because of this catalyst we can only have these intermediate forms. So at equilibrium, no, it's very expected that carbon oxides and water will be our most abundant species. Yes.
Okay, thank you. Great presentation.
Thank you.